Your classifier can stay accurate, but its probabilities go wrong when class mix changes. You'll see how to connect the pieces into a workflow that spots a changed class mix and corrects class probabilities. I'm Professor Pi, teaching AI foundations with simple Python. Label shift is a very common blind spot in deployed models. You train on one class balance, and later users send a different mix. The separator the model learned can still work, but its probability outputs get biased by the changed priors. That breaks calibrated thresholds, monitoring alerts, and any business rule that expects correct population probabilities. Practically, we want a lightweight way to detect that shift from unlabeled production data and adjust probabilities without retraining. Black box shift estimation does exactly that. Treat your classifier as a black box that reports predictions or probabilities. Learn how it behaved on labeled source examples. Observe how it behaves in deployment, and infer how the class priors changed. The result is an estimate of the new class prior and a rescaling of probabilities so averages match deployment reality. Think of a simple picture. You trained where class 0 was common, but in production, class 1 is common. The model still recognizes patterns, but it was tuned to the original mix. BBSE asks, given the model's mapping from true labels to predictions on the source, what mix of source classes would explain the observed prediction distribution on target data? If you can answer that, you can rescale probabilities to match the new mix. We'll build a tiny pipeline to show the full idea. First, we make synthetic source and target labels with different mixes. Then we train a simple black box classifier and record its predictions on source and target. Next, we compute the confusion from true to predicted on the source, solve a linear system to estimate target priors, and finally reweight the model probabilities to reflect the estimated mix. The goal here is to spotlight the core math and the correction step. Quick note, this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. Now, we will generate the toy data and show the true priors, so we have an oracle to check later. This snippet uses NumPy to show the labeled prior change BBSE is meant to recover. The source population has many more class 0 examples than the deployment population, even though nothing here says the feature patterns changed. YTGT true is included only as an oracle check for the tutorial, because real deployment data usually does not have labels. np.binCount turns labels into class frequencies, which gives us the clean target we will later estimate indirectly. The output shows the source and target priors, setting up why unchanged classifier behavior can still produce wrong deployment probabilities. Next, we train a simple, interpretable black box, so its behavior is easy to inspect, but still realistic. This example trains a scikit-learn DecisionTreeClassifier as the black box BBSE will observe. The model sees one interpretable feature, XSRC, and learns a one-split decision rule because max depth equals 1 keeps the behavior easy to inspect. That simplicity is useful here. BBSE does not need to know the tree internals, but we can still reason about its mistakes. Accuracy score gives a quick sanity check that CLF has stable class conditional behavior on the source data without being perfect. The output shows the classifier is usable, while still leaving room for BBSE to correct population-level probabilities. With the trained black box, we can measure what it reports on unlabeled target data and compare to its source behavior. This code uses CLF predict and NumPy counting to detect shift without reading target labels. The target feature values in XTGT follow the same kind of class conditional rule as the source, but the class mix is different. CE is the black box prediction distribution on labeled source data, while TGT scene is the same measurement on unlabeled deployment data. Shift score is computed as a compact distance, even though the print focuses on the two visible distributions. The output shows the classifier is predicting far more class 1 in target, which is the observable signal BBSE uses. Measuring the black box confusion on source gives the mapping we need to invert for the target mix. This snippet estimates target priors by solving the BBSE equation with NumPy. C stores how often each true source class becomes each black box predicted class, so its columns describe source class conditional prediction behavior. np.linalg.solve asks which target class prior vector would explain TGT scene through that same behavior. np.clip and renormalization are practical guards against tiny negative values from noisy estimates, especially with small samples. The output shows BBSE prior matching the Oracle prior in this controlled example, which is the key bridge from detection to correction. Finally, we apply the estimated prior to adjust the model probabilities so they reflect deployment prevalence. This example applies the BBSE correction to scikit-learn probabilities from clf.predictproba. The raw probabilities still reflect the source training mix, so their average positive rate can understate the deployment population. Weights divides the estimated target prior by SRC prior, then fixed rescales each row and renormalizes it back into valid class probabilities. This changes population calibration while preserving the black box ranking within each probability pattern. The output shows the mean positive probability moving from the raw model average to the BBSE estimated deployment prior, completing a tiny detection and correction baseline. In a real project, you would map this toy flow to your model and logs. Compute source confusion from a labeled validation set. Periodically collect unlabeled prediction histograms from production. Solve the same linear system on those histograms, and reweight saved probability vectors before triggering downstream actions. This method treats your classifier as a black box and estimates new class priors from prediction histograms. Use it when class conditional behavior is stable, but class frequencies change and you have unlabeled production data. One caveat: if the model's class conditional accuracy changes between source and target, the estimate can be biased. To push this further, pick a real dataset and make the evaluation concrete. For example, use the credit fraud dataset and measure how BBSE prior changes when you simulate a twofold increase in fraud rate. Recompute the source confusion on a stable validation split, and compare corrected probabilities by looking at calibration and expected cost under the new mix. If AI Foundations in Python help, subscribe and watch the AI Foundations videos.